All right, hello. I think one of the things I wanted to do here was just give an overall architecture of at least how I understand our code base today and our most important parts of the system today, because I realized we probably haven't seen that put together yet, and it's all kind of coming together on the spot. So I'll show you what I have. Some of you might have seen this macros diagram, this crates diagram that shows the control flow of crates. I think that is useful, but I think it's also useful to have a overall structure. And if there are any inconsistencies, we can just change that as we go. So first things first is we have something that's called a BAML project. And there's a few certain attributes about a BAML project. It is fully incremental, and it is going to be built off of raw source files and other information. But the most important part is it provides access to the compiler and everything else underneath. I'm going to ignore all the implementation details of how it works. We'll just assume that we have a BAML project as a top level node. We have a couple points of surface area that come out of here. The points of surface area as I understand them, and I'll make surface areas green, is going to be a WASM interface for the playground. And then we'll also have another interface on top of this. And then we'll have what I would call language clients. And language clients basically play into a couple of different things, but they have their subsections of PY, let's make this better, PY, TS, and then CFFI. If we were to at some point introduce WASM, would be another peer to these rather than independent, and it would work off of this. And then on top of this, we have one more thing, which is going to be what I would call BAML client, and this is language specific. So I'll put lang BAML client over here that describes this over here, and I won't make this gray. I'll make this kind of different because it's not going to be pure green underneath the hood. So, and then we have language clients over here. Well, what comes next? Well, the thing that happens next is we have a separate thing. We have what's called the BAML runtime in our existing code base, but for now, we're not going to be calling it BAML runtime. What we'll be calling it is going to be BAML Executor. And I'll describe why it's called the Executor in a second, but you should assume that this is the interface that has everything called render prompt, etc., etc. Now, the question is, BAML Executor is not incremental. BAML Executor is not at all incremental. It is statically defined. So how does an incremental BAML project feed into a BAML Executor? Well, we have something called a BAML program. And a BAML program is something that can be produced from a BAML project, but is not necessarily a BAML project itself. Additionally, a BAML program can be used almost as a peer to an executor, and arrowhead is the wrong thing. It can be used with an executor, but it's not necessarily an executor itself, if that makes sense. So you can apply an executor on a BAML program, but it's not the executor itself. A BAML program is kind of incremental. That's probably the best way to describe it. It's not actually incremental itself, but it is kind of incremental. Now, what does that mean? What that means is the following. It's not incremental in the way that salsa is incremental. This is incremental because salsa. This is incremental because we have methods like update program, update function, update class, etc. So this is incremental because of the methods it exposes. This is incremental because of salsa. So at any point, you can always turn a BAML project into a program, but the way that a project turns the program is by giving you diffs almost, and then you apply those diffs into the BAML program and say, this function has changed, this function has changed. And that is how this works. Now, that works nicely because of bytecode behavior, and that we don't actually have to go produce the same bytecode along the way, and we're allowed to have things like render prompt still be incremental, because the thing that exposes render prompt is BAML program. So BAML program ends up being the interface that has a bunch of methods on it or capabilities on it that end up being used for these two systems under the hood. Now, we might choose to put another layer on top of this if we want. That's just like some sort of actual interface on top of this that actually sits over here that kind of mudges, that assembles the two of these together, that takes a, sorry, let me move these up. That kind of does the assembly of the executor and the program together and provides interfaces like render prompt, render test case, understand all that stuff. But that's basically the whole gist of this. Now, how does the BAML executor work, and how do we actually merge the VM with LM runtime and system calls like fetch and everything else? Well, let's talk about that really quickly. So we have two types of things. We have what's called the BAML VM. We have what's called the LM runtime. I'll just call it LM ops for now. And then we have what's called BAML sys. And I'm going to make these all orange because they plug into the executor. This has nothing to do with the compiler. This is purely to do with how things execute itself. Well, the way that this works is the BAML executor is responsible for driving all of these things together. Oops. The BAML executor controls all this. This is actually very similar to how our current executor works. And I'll show you what things live in each one. The VM is responsible for actually doing VM instructions. So functions defined with VM bytecode all execute through the VM. The LM ops is responsible for doing all things related to LMs. I don't think we have a clear understanding of what all these things are, but I think over the next few days, as Sam and Antonio make more progress, we should have a really clear idea of what BAML LM ops needs to do. And then BAML sys is what you can think of as all network calls, so like fetch, file read, file write, bash, or like shell, pwd, etc. all live through BAML sys. Now, as you know, we have a whole slew of things that interface with this. So we have WASM interfaces, and then we have BAML language client interfaces. The problem is BAML sys is actually plugged in through many different ways. In the case of WASM, when we're doing the BAML playground, we actually have to go all the way through VS Code, send some of these stitch requests through there and proxy everything. Rather than doing it in the way that we've been doing it right now, we have a new way to go do this. BAML sys has a special method called register methods, which basically takes in register method, which takes in a name and then a callback to associate with how to actually implement each of these calls. It's not defined in BAML sys. BAML sys is an interface. And what we do during WASM time is we actually just register methods for each of these all the way through here for how to register BAML sys. And we register every single method along the way and say that fetch has to be fetch returns this, file read returns this, file write returns this, and we're able to implement it. This gives us a really nice way, this gives us a really nice way to actually go ahead and make this super modular and make this totally agnostic of whatever runtime engine we're doing this in. So if we end up supporting Cloudflare workers, for example, this will also just work because we just have to change how BAML sys gets registered based on what language clients that we're targeting along the way. Cool. The other benefit here, I'll talk about that in a second actually. Let's talk about how these work now. So what happens when a BAML program executes? Well, when a BAML program executes, the first thing that we do is we call function. Call function determines how we call the function. The function is either going to be an LM function or a VM function, and it just gets it from the program's perspective, it just calls it. The executor then says, I have an instruction to run. The instruction says run VM code. So then I run VM code. And eventually the VM code says, I want to run a special instruction that's a BAML sys fetch instruction. So I register BAML sys fetch and I give it back to the executor, and the executor pauses the VM with that program counter at where it is today, and then pauses and then hands it off to BAML sys. BAML sys completes and then completes the promise. And the executor sends it back and round trips this here. Now, and then it does the same thing. A VM says, I want to do LM function. It does the same thing. It renders this all the way down, sends it to BAML ops, and LM ops finishes the thing. It handles the promise and goes down into here. If we want to support things like streaming or everything else, well, the nice thing about the alt is it's all centralized through BAML executor. So none of these things should have interfaces through here. And instead of having a layer of BAML executor calls, what we had before is we have BAML runtime and BAML VM runtime that can nest in each other in weird ways. In this case, we have a very flat structure. So it should be much easier to organize and understand. We're also going to try and do our best to make sure that tracing, which I think we have put almost little thought into so far, which is totally okay. We'll have to come up with a way for how tracing fits into here, but I think tracing can also be a thing that lives in BAML executor. And since all these things will have relationships over here, all we really have to do is just make it so that if anyone ever pings the tracing system from any of these systems, it just sends a request to BAML executor and says, I want you to trace this through some way. And BAML executor just gives it to the tracing module, which can be totally responsible for communicating with the web and lives as a separate ad hoc system. And then BAML executor can also make this a no-op in the case of tracing not working. Now, on the order of tracing, one of the pain points that we've had along the whole way is we have two different ways of doing fetch, and that leads to different problems. For example, once we have the VM code and we're doing fetch, in the BAML playground, we currently proxy a lot of network requests because of CORS errors and everything else. If everyone writes VM errors here, we're going to get tons of CORS errors through any code running through the playground. Well, the problem is we're actually using two different types of fetch. We're using fetch differently in LLM ops as we are in the VM, because the BAML VM calls a fetch instruction, which triggers BAML sys, but BAML LLM ops just uses that. So the way to solve for this problem is actually take a dependency directly in LLM ops on BAML sys. And if we take that dependency, then every single time we make any sort of network request, we can actually take it directly from BAML sys itself. So instead of calling it request, we'll always call it through sys. And what this does is any register method call that is made here will be really clean. So for example, today for supporting multiple LM providers, like GCP auth or AWS auth, we use AWS CLIs and such around here. We do a lot of plumbing to push that through into here. Well, we don't have to anymore. Because we have a shell command available in BAML sys, which we will have to build anyway, because if we want to support AWS support through here, it's required. Well, we can just shell through the BAML sys : shell and just call that method and return this all the way through here, and it should just work because register method will have registered these. The other nice benefit is if any method is not registered, it can either have a default implementation or it can also just say that I'm going to error out, and it will just plumb through the error mechanisms we have built in for all the other tools along the way with no additional work on our end. Now, one other thing that I'd like to talk about before we go do this is actually testing. So how does test case rendering work? So we have our playground. In our VS Code, we have two different things. We have the source code on the left, and then source code, and then we have the actual playground on the right side. Let's say I have a playground, and whatever kind of function this is, whether it's an LM function or whether it's a expression function, doesn't really matter. Whenever I have a playground, there's two tasks that we have to do. I'm going to try and render the function in some way. As a part of rendering the function, whenever I click I need to first get test case args. Once I get the test case args, I may need to evaluate them and actually execute some code. And then after I do that, then finally given the evaluation of the test case args, then I will want to, in some form factor, render the function. Whether that means executing it, whether it means showing the visualization graph, whether it means showing the prompt, doesn't really matter. I want to do these three things. Now this ends up being really tricky. So for example, let's say I did this and I have a math.random. So get test case args is static. No computation is happening here. It's well understood. It's all get test case args says args is a thing that's called the load data function, and that's getting the args. But when I actually evaluate them and I want to consolidate what the args are expressionally versus what the args are as a function, as a value, I will probably need to go and actually evaluate this. In this case, imagine that this is a 30 gigabyte file and this is a 1 megabyte file. Clearly, now I have huge performance implications as I move my cursor around, because every time I move my cursor, if I were to evaluate this, math.random gets reevaluated. And every time I'm loading 50 gigs, I'm loading 30 gigs or a meg, and my experience as a developer is atrociously going to be hampered because I really don't want this to trigger almost all the time. Then I need to go render this. So imagine I'm rendering the prompt. So clearly, if I likely don't want every single time I move my mouse for this to be re-rendered and recomputed every single time. I also probably don't want to accidentally read a 30 gig file and have the whole system hang. So there's a couple of things that needs to happen here. One is once test case args are evaluated, they kind of need to be cached to some degree associated with this and not recomputed again, and the cache needs to be somewhat dependent. So evaluation of test case args needs to be incremental to some degree. Whether it's incremental through Salsa or whether it's incremental through some method that we have, like BAML program, doesn't really matter, but it does need one of those two solutions. And then two, we likely don't want to do mutable operations during test case evaluation, for example, file.write, without user approval, because just because I move my cursor to some location doesn't mean that I suddenly want a post request to fire off. I may be okay with get, but I may not be okay with post. So I may want to control that. Or you can imagine that this is an LM function that runs this. I may not want to spend money just by moving my cursor every single time. So we likely need some sort of control flow that says, hey, I want to execute this code whenever possible, but if I do something dangerous, I want some human-in-the-loop control to let me press a button that manually approves the workflow at that point. So the good part is, because all these dangerous requests are always going to end up going through some BAML sys module, file read, file write, fetch, post kinds, etc. BAML sys can have a protection layer built into it on top of itself. Oops. That's a validate async fn allow check approvals. It can take in methods and stuff. And this can be done through a messaging system. So BAML sys exposes through BAML Executor a messaging system that goes through and gets approvals for various methods and various constraints. And we can write heuristics. If it's a 1 meg file, let it fly. If it's a post request, require approval. You can have approvals like Cloud Code that are dangerously allow and just has a checkbox that just screw it, just let it run whenever you want. Or you can say that, hey, for this test case, we are approved and this works. And the best part is these approvals can be default false in the BAML playground for a lot of the default scenarios that are dangerous, post, reading large files, etc. But totally allowed and passed through in language clients. So it basically becomes a no-op in that scenario. So it should effectively work in that way. And then the playground tool, or whatever WASM playground is, can be responsible for actually storing the evaluated test dogs. But again, one of the big designs here is we are mixing declarative code with imperative code. So we need to be really careful about how this interleave happens. And I think we have an architecture plan that will help support this. And hopefully we'll get an answer pretty soon from Antonio if this is working or not. I think this video has already gotten pretty long, but hopefully this gives everyone a pretty good idea of what happens and where incrementality lives and where static items live, and gives us an idea of exactly how we're going to start executing this code in a variety of different conditions. There's probably still a ton of open questions, and it's still going to be a big discovery process to see exactly how we have to go solve some of these problems. But I think for now, we should all have an understanding of what happens.